So, how do we know? How do we know what's inside Earth? Let me just give you a taste. I could give you a word. What's the word? Evidence, right? Evidence. Lots of detailed evidence. Scientists don't just sit around agreeing with each other. We challenge each other. It's kind of like playing basketball. You don't want someone that's not going to challenge you. It's no fun. So here's 4 points to make. One is, there's a clue, big clue. We use this a lot, talking about Jupiter or anything. And that's planetary differentiation, which we talked about last time. Dense stuff, as things form, the dense stuff will sink to the center. So we expect metals with rock around it and lighter rock. We expect it to layer out. And you can do measurements of gravity and so on to test some of the details. So planetary differentiation is a big clue. Now you might want to just drill down. Why don't we just drill down and find out? Well, there's a problem. It's hot. And when you drill in with metal and the metal gets hot, well, you saw what happened. Our outer core is liquid. It's liquid metal. It's so hot down there that our metal drill will get soft. It's very hot, right? It's also far. How are you going to make a drill that big? How do you get down there? You look for places where the crust is a little thinner, sure, and you go down. But we've only drilled down, anyone know? Well, less than 10 miles. I'll leave it at that in case we find a way to go deeper than we have now, but less than 10 miles. So, I mean, that's good. We can learn stuff. But suppose that doesn't get you down into it. Maybe you want to know what kind of pie this is. What is this pie? I got to go in. But if you're still in the crust, you don't quite get down, how do you know? Well, you look at what comes up. Volcanism. Volcanism comes up. So instead of going down, you just wait for it to come up. Look, it's berry pie. It's an apple pie. What comes out? And what you get is gas, and you can analyze the details out of that gas. And you get lava, hot rock. You can analyze the detail, the different rocks, and so on, and all around. And you just years, decades of analysis of what's going on. So we do know that, though. You've got this. That's good. But there's a really good one. If you crack your arm, you tell your friend, I fell down. I think I might have cracked a bone or something. And they get out a knife and say, let's look. You go, that's okay. I'll go to the hospital and they'll x-ray it. They'll send in x-rays, waves, that image the bone. I don't need to look at it with my eyes. I can image it and see whether or not it's cracked. And so too, Earth has a natural imaging process called earthquakes, driven by what? The convection in the mantle. Remember that cycle of the movement. And when it shifts, it sends out two types of waves. And those image the interior. This is a big deal. Let me show you why. So there's two types of waves, P waves and S waves. P waves kind of go back and forth like this. I hope you can see that. And S waves are kind of like this. And they both happen when an earthquake, little shift happens. P waves, I say, wiggle back and forth as they travel. They're called P waves, they're primary waves. And the reason they're called primary is they're faster than secondary, so they get there first. Primary, first. And these kind of waves can go through air. My vocal cords are vibrating. The air here vibrates. It vibrates this air. It vibrates that air. It gets to the microphone, and so on. And then we do the funny thing that we do with electronics, and then it comes out your speaker, and it vibrates and hits your ear. It goes through the air. It goes through liquid. So primary waves, they're faster, and they can go through solid and fluids, and a fluid is a liquid or a gas. So they'll go through, fine. What about these secondary waves? They wiggle up and down as they travel this way. So instead of going like this, they go like this. And they travel kind of like that. They're secondary because they're slower and they arrive second. Fine. But the interesting thing is that these type cannot go through. They can be on the surface of the ocean, but they can't go through liquid or gas. And let me give you just a taste of how that plays out. Didn't have that there for you, did I? Sorry. All right, you can pause. Right. Suppose you have an earthquake here, San Francisco, California. Earthquake. You got detectors around, and they pick up these wiggles and they pick up these wiggles, and they measure them. And guess which one they get there first? The P wave, right? So a P wave gets here first, and then the secondary wave gets there, the S wave. And you time the difference. How long did it take for the S wave to get there after the P wave? And since the P wave is going faster, it'll start pulling ahead more and more. And so the farther away you are, the more time it'll take for the S wave to catch up and arrive. And so if you're farther away here, the P wave, the primary wave, gets to the detector through Earth's mantle here, and the S wave is lagging behind, and it takes longer for the S wave to arrive after the P wave here, shorter here. We can do that calculation. We didn't do it here. And we can figure out how far away the earthquake was, where it started. And if you combine all the detectors, you can figure out where it started. That's how you do it. You got the P wave, and how long does it take for the secondary wave? Now, the other interesting thing, though, is that, well, of course, it goes in all directions. And we send a P wave. And the P wave comes over here. The P wave of the earthquake. And the secondary wave. Before I do this, you might see where I'm going. The S wave, secondary, is not an aftershock. An aftershock will also send out a P wave and an S wave at the same time. Okay, not each shock will do that. But guess what happens? The S wave can't go. You go, hey, where's the S wave? There must be some liquid or gas between us. And you can use this, and in fact, it bends here like light. If you stick a pencil through in a glass of water and the light bends, we call that refraction. And the details are quite impressive, I gotta say, man. They're really impressive. We get into geophysics and that sort of thing. Nonetheless, I hope this gives you a little taste of how we know what's inside Earth. And again, it's a pretty detailed thing, but rather than slicing open our arm and seeing if we cracked our bone, or slicing open Earth and seeing what's inside, we can use imaging techniques to find out what's inside. So it's a good question. That's a very brief answer to that. Now we will go on to the next level. Let's see, where are we now? Let's go back over here. Ah, yes. Earth. So, what we have done so far, set this up. We have done what a pretty blue world, but it's more than just the surface. We're a little grain of sand. We're so small, and yet it's so wonderful. Isn't it amazing how wonderful the music that humans have created? You know, the toil, the folly, the bad, the good, the beautiful. We talked about the 6 layers and think about how the beautiful surface is related to what's inside. We've done the 3 interior layer. What's up in each layer? and how we know. In the next video, we'll talk about our surface or crust, the 4 things that change the surface. We've already talked about tectonics and volcanism, that's 2 of them, so it's not going to be too bad. And I'll mention very briefly about water, and then we'll jump to magnetism and go to atmosphere, and you will have a good sense of this planet, and that will be adequate to study other worlds.